Okay, welcome back. This is the 12th week of online lecture, and so far we have studied the electricity and magnetism. So we learned the electric field and also the magnetic field, and we finally learned that these traveling waves of electromagnetic fields become light. Okay, so light is, as I said before, is the subject of optics. And actually, chapter 34, we are skipping chapter 34 because chapter 4 is about optics, which is about, say, lenses and mirrors. So those are the things you probably have learned in high school. And there's nothing much new to learn in high school, so we are skipping it. But instead, we are going to study very interesting phenomena involving this light, which is an interference in this chapter and also diffraction in the next chapter. Okay, so here in chapter 35 we are going to study interference. Okay, let's make a review first. In the last week we studied 2 chapters, and from there we learned the Maxwell's 4 electromagnetic equations, and we also learned the speed of the electromagnetic wave propagation. It was actually a constant. It was equal to 1 divided by square root of the product between permeability constant and permittivity constant, right? Okay. And we also learned that these electromagnetic waves are in fact light waves, and they are transverse waves. The electric field oscillates perpendicular direction with respect to the direction of the wave propagation, right? Okay, and using these transverse light waves, we learned how to polarize these waves by using polarizers. Okay, and in this week we will study the Huygens principle for waves, and then using it we will also learn the laws of reflection and refraction. And in doing so, we will learn the concept of the index of refraction. Okay, and we will also study the phenomena called the total internal reflection. And finally, we will discuss this interference and diffraction of light waves. Of course, the diffraction is what we are going to study in detail in the next chapter, but in the last part of this chapter, we will see the simplest case of interference and diffraction. Okay. So in the previous lecture, we learned that light was a transverse electromagnetic wave. So in this figure, if this is the direction of the wave traveling, then this sinusoidal part represents the electric field, and this part will be the magnetic field. Okay. And then the distance between these 2 peaks is the wavelength. Okay, but then the real waves actually do not look like arrows here. If you look at real waves, it really looks something like that. So here the wave is traveling and something is oscillating up and down, and what you will actually see is instead of this arrow, you will see extended line like this, which is actually perpendicular to the direction of the propagation, which means that this whole line will advance. Okay, so this is what we mean by wavefront. So wavefront is an extended line which is perpendicular to the direction of the traveling. Okay, so in this figure, if I try to draw a wavefront, it will look something like this or like that. So wavefront can be anywhere, but it is probably the most convenient to pick the highest point and draw this way, because this is the most visible, for example, in this figure. Okay, and then now let's talk about Huygens principle using this concept of wavefront. And this Huygens principle is a very important principle for all kinds of waves, not just light waves, but it is good for any wave. Okay, and what it's saying is that all points on a wavefront serve as point sources of spherical secondary wavelets. Okay, can you understand what it means? So let me explain it using the figure here. Okay, now, okay, suppose one of these wavefronts is this. Okay, this is one of the wavefronts, and after some time, this will of course advance. And what is actually happening is that all the points along this wavefront actually create secondary spherical wavelets, meaning that small secondary wave which looks like a sphere. And then of course in two-dimensional figure here I have to draw it just like a circle, but in 3 dimension it will be spherical. Okay, so for example this point will create a spherical or circular wavelet like this, and this is advancing. And at the same time another point here, it will also create a spherical wavelet like that, and this point will create independently these spherical wavelets, and all of them do the same thing. And what we actually see is a summation or combination between these spherical secondary wavelets. So after some time it will look like this wavefront has moved up to here, but what is actually happening is instead of this whole wavefront moving forward, each point creating secondary spherical wavelets, and then what we see is simply a summation between them. Okay, so this Huygens principle is good for all kinds of waves, just like I said, and at the same time it is good not only for a plane wave like that, but it is also good for circular wave like this. So this figure looks more like that, and what is actually happening is that it kind of looks like this circle is advancing to here, but at the same time what is actually happening is that each point along this circle creates its own small circular wavelet, and finally what we see is simply a combination of them. So it looks like whole thing is advancing, but what is actually happening is that each point creates small circular wavelets. Okay, that is the Huygens principle. Okay, this time we will perform a simulated experiment on reflection and diffraction of light. Okay, so here I have a laser source. As you can see, this red laser beam goes into the interface between the air and water, and a part of the laser beam is sent back into the air, and this part is called the reflection. Okay, and the other part of the beam is going into the water, so this part is called the refraction. Okay, so here we will study the relations between the angle of reflection and angle of incidence and the angle of refraction, depending on the properties of this air and water. Okay, so let's turn the laser beam on. So as you can see, as I just said, we will study the relations between the angle of incidence, which is here, and angle of reflection, which is here, and also the angle of refraction, which is here. So remember, these angle of incidence, angle of reflection, and angle of refraction are all measured with respect to this vertical line. Okay, this is not the angle of incidence. This part is the angle of incidence. Okay. Well, the first thing you can immediately realize is that this angle of reflection looks to be equal to the angle of incidence. Okay, actually that is always true. So however small or large you may change the angle of incidence, you can see that this angle of reflection always remain equal to the angle of incidence. Okay, that's the first thing. And then how about the angle of this refraction? As you can see, the laser beam is not straight here, it's bent, which means that this angle of refraction is different from the angle of incidence. And in this particular case, this is actually smaller, right? And when you are trying to change the angle of incidence, this angle of refraction always remains smaller compared to the angle of incidence. Okay? And then the reason why this is actually smaller is because of the quantity called the index of refraction. Okay, so here we can see that the index of refraction for the air is equal to 1.0, and the index of refraction for the water is 1.33. 1.33 is larger than 1, and so as you can guess when this index of refraction is larger, this angle of refraction becomes smaller. Okay, so we will later see the detailed relations between this index of refraction and the angle of refraction, and of course we have to explain what this index of refraction is. Okay, so please wait for that. And here we have a convenient tool to simulate the change of the index of refraction. Okay, now suppose you actually try to increase the index of refraction for the air larger than 1. Okay, let's see. As you can see, okay, in this case, the angle of incidence is not changing, so therefore the angle of refraction always remains equal. But you can see that when I change the index of refraction of the upper part, which was originally air, the angle of refraction is changing, right? So this suggests that the angle of refraction is related to the index of refraction of the upper part and also the bottom part. Okay, so it actually suggests that this angle of refraction is related to the ratio between these two indexes of refraction. Okay, and then let's try another very interesting thing. I will fix it to 1.33 and make this upper part of the index of refraction, let's make it closer and eventually equal to the bottom part, which is 1.33. Okay, if I fix it at 1.33, now you can see that it finally goes in straight without bending, right? Okay, and then now let me try to actually increase it further. As you can see, okay, now the angle of refraction on the bottom part is larger than the angle of incidence, right? And then this is because now the index of refraction is larger on the upper part. Okay, so this is an interesting case, so I will keep increasing it, and as you can see, this angle of refraction keeps increasing, and finally there will be a situation where it actually approaches 90 degree, and finally what happens? Now this refraction completely disappeared, so therefore as a result all the light will be reflected back into the air, right? Okay, now this time this is not air, but anyway the light is now completely sent back into the upper part. Okay, now this is called the total reflection, or sometimes called the total internal reflection. Okay, we will try to explain this in the next slides. Okay, so let's try to summarize what we have seen in the previous simulated experiments. There we had this light wave coming into the interface between the air and the water. So part of the beam was reflected back like this. Okay, so there the first thing we have seen was the law of reflection, which states that the angle of reflection is equal to the angle of incidence. So this angle theta 1, which is the incident angle, is equal to the theta 1 prime, which is the reflected angle. This is always equal. Okay, then how about the second law of refraction? Okay, so this is about the angle of refraction for the beam going into the water. But in order to explain this law of refraction, we actually have to explain the refractive index first. We didn't explain what this refractive index is, right? Okay, so let's do that. This refractive index, or the index of refraction, is defined like this. So this n is the index of refraction, and c is the speed of the light in vacuum, and v will be the speed of the light in this particular medium. Okay, so what it suggests is that the speed of the light is constant only in vacuum. So as soon as light enters any medium, the speed of light is no longer c, it's different, and most of the time it slows down. So now we can say that the refractive index represents how much the light is slowing down in a transparent medium. So the more it slows down, or the slower the speed it becomes it will have higher refractive index. Okay. And then now let's see what's on other result of this refractive index. In order to discuss it, first we have to understand that actually the frequency of light does not change even when it enters a different medium. Okay, this is something we have to remember, and this is important because always for any wave, the velocity is determined by this wavelength multiplied by this frequency. Okay, so this frequency is not changing, and then now we have just said that the light speed is changing depending on the refractive index, right? So therefore, using these arguments, now we can see that wavelengths of the light actually also changes. So now let's try to write the wavelengths of the medium, wavelengths inside the medium which has a refractive index n. Okay, so then according to this formula, now we know that this wavelength is equal to the velocity divided by the frequency, and this frequency is equal wherever the light is. Okay, so therefore even in the vacuum the frequency will be the same, so therefore we can actually use the speed of the light in vacuum divided by the wavelength of the light in vacuum. Okay, and then once you have written that, this part which we rewrite here actually correspond to the index of refraction. So therefore now we get the relationship that now the wavelengths of the light inside the medium of refractive index n is actually the wavelengths of the light in vacuum divided by the refractive index, and this refractive index is typically larger than 1, right? So therefore now wavelengths become smaller. So just like here, so when the light is traveling in medium, and if in these two parts of the medium on the right side has higher refractive index, the wavelengths inside it will become shorter. Okay, that's what it is. So remember that refractive index is defined this way. So if the light is slowing down more, it will have higher refractive index. So therefore, actually, we in the previous similarity experiment, we have seen that the refractive index of air is just 1, which means that inside air, light doesn't really slow down much. So its speed of the light in air is almost the same as the speed of light in vacuum. But when the light enters the water or glass, it will slow down quite a lot. Okay. And another thing we have to mention is that this refractive index also depends on the wavelength of the light, which means that even inside the same medium of the same property, refractive index is actually not a constant. It is different depending on the wavelength of the light, and typically if the wavelength is shorter, then refractive index will become larger. So for example, blue color light will almost always have a larger index of refraction compared to the red colored light, and that is why this prism can separate the white light into the colors of rainbow. Okay, so in this case, because the blue color, which has a shorter wavelength, has higher refractive index, actually it will bend more. Okay, why does it bend more? We will see in the next slide. Okay.